Okay, so I would like for us to be able to build this algorithm called the perceptron algorithm. We have all of the basic tools that we need, and I really would like to have some feedback from you as we're building it, so that I know if this is too much or too fast. So let's go. I'm going to go really slow, and please speak up if you have questions. So let me set the stage first. And again, so suppose we have n points of data. Let's just suppose that. Say, and I'm going to use superscripts to count the things. So that's x1, y1, dot, dot, dot. Capital N, where xi is a d vector of features and yi is the label of feature vector xi. So this is our setup. We have data and we have label for each of those things. Okay, nice. I can see your face on the camera now. Okay, all right. So, and for our sake of simplicity, we'll say that so yi is the label of feature vector xi, and yi can only be one of two choices. Can only be one of two choices. Which means that this is, the labels are binary. There's only one of two choices. And for our sake, let's just use blue and pink for the given features, okay? So what the goal is going to be is that the problem at the end so we want to use this data to predict the label for a given feature vector not in our set, or a feature vector not in our set of vectors. That's our problem. We want to use this data to predict the label, and our prediction is going to be a function. We're going to build a function that's going to make that prediction. Okay, so we can think of, so by the way, I'm just setting up the problem. I'm assuming I'm going to get some questions here in a moment. So just speak up if you do have questions. We can think of the features as a input signal. okay? And so imagine that your brain is receiving signals, okay? Imagine your brain consists of a single neuron, and there are dendrites connecting it, and through those dendrites, there are electrical pulses that come in. And if those pulses are strong enough, your brain decides to do something one way or the other. It's a very simplified model. In particular, we can think of this. Suppose that each of our feature vectors consists of two things. So if we input the first feature from the ith vector and the second feature from the ith vector, you can think of these as like numerical signals coming into a system. Okay. And then we can weight those signals and introduce what's called a bias. So we'll just throw in the number 1. So this would be the third weight. We can throw these numerical signals, and this is like a vector, right? That's our feature vector. We can throw these into the system together with a 1 for the bias. And then we can output a 1 or a negative 1. So 1 would be for a blue or pink for a negative 1. Because we have to represent everything by numbers. So here's the idea. We take the first feature and we give it a weight. And then we add that with the second feature, also weighted. And we add a bias. If that is strong enough, we're going to send out a 1. And if it's not, then we'll send out a negative 1. Does that make sense, like from a neuron perspective? That you have an input signal, which is a vector, and then you weight each of them, and then add a weight for a bias. And if that combination is great enough, then we say fire a 1. If it's not, we fire a negative 1. So in particular, if our feature vectors consist of 2 features for each vector, then W1 times xi1 plus W2 times xi2 plus 1 times W3. If that's greater than 0, we want to predict a positive 1. So that's like our threshold. If that sum is positive, we're going to make it a 1. If it's negative, then we're going to predict a negative 1. Are y'all okay with that? We don't know how to pick the weights yet, but I'm just saying the model itself.
Yeah, all 3 of these WX's, right, are inputs of the same, or features of the same input, right?
The X's are features of the input I.
Yeah, okay.
In the weight,
so all of these are occurring for each of our inputs, and then that's kind of forming our clusters.
Well, not precisely. The weights are we're going to tweak these weights over time. We're going to basically, well, let me go ahead and say that instead of writing this over and over again, we can just take this combination and look at the sign of it. Which is our prediction. predicted class or predicted label. And the sign is just, if this is greater than 0, it's a 1. If it's less than 0, it's a negative 1. Okay. Now what this is doing, right? If the weights were all perfectly fine-tuned, then, so, like, all right, so this is like kind of like a more concrete example here. So, if x1 was equal to just like x11, x12. Well, actually, that's going to take too much notation. I would say if y1 was equal to positive 1 and y2 was equal to negative 1, our hope would be that we would predict a 1 and we would predict a negative 1 for that input. Because we know the labels, we can check our predictions against the known label. The only thing that we have to tweak around with, to mess with, are these guys. We can tweak the weights to do better at our predictions. We can choose them randomly at first, which, by the way, this is so messy to write. What we really should write for this is that this is for y1, we're going to predict on x1, or w times x1 plus the bias. The bias is really w3, but so it might help actually to like show you this computation. Like actually look at before you train the model, you like how it's set up. So let me double check something. Let me pause the. Okay, so I found the data set that I want. Oh. So let me share my screen. So we're just going to use the iris data set again to get this kind of started. So it's here. I'm just going to make a new Python. Okay, so as before, import pandas as PD. All of you have this. Import this data set, by the way, numpy as MP. And then I'm going to say iris is equal to PD. Almost forgot. Probably going to do some plotting. Read CSV. Iris data.csv. I think that's what I called it. Okay, so let's just, I'm just going to get some just two features. So I'm going to say, how can I do this? So data is maybe equal to, so I'm going to have, so x is equal to, say mp dot array of, say, x0, comma, x1, comma, and then 1.0 for the bias, and I'll explain that in a moment. For x in zip iris dot sepal length from 0 up to 100. I'm only going to look at the first two species to keep it a binary classifier. Iris dot sepal width up to 100. So let me just make this a little bit neater so we can see. There's the zip. And then I'm going to get all the labels, which are so the first 50 are ones. So setosas, I'm going to call ones. And the versi colors, the other ones, I'm going to call negative ones. So I'll just show you what the actual labels look like. Line labels. Say X for X in iris dot species up to 100. No, I forgot to close that off. So X are just the first two features, and then Y labels. Are the types of flower, and you see either setosa or versicolor. I need to change those to I need to change those to ones or negative ones. So I can say, I can write a function to do that real fast. So change. So it's going to take in species. If species equals setosa, return 1.0, else return negative 1.0. So then I'm just going to make a, so species, or no, sorry, change species for species in Y labels. So now all of those should have a numerical value associated with them, 1 or negative 1. Okay, so notice that, so inside of X, we have feature 1, feature 2, and then the 1. The 1 is going to serve as the input to our bias input, right? Or the intercept of our function. So now I need some weights. So I'm going to say weight equal to np.random.rand3. So what this makes is, actually you should do rand n. The difference is that now these are chosen from a normal distribution, which is what you should do when choosing random weights. So now notice what happens between the weights and the features, right? So like x0, I'll say weights inner product x0. It's a negative value, right? But what is the label for the 0 entry? It's a positive 1. What about there? Doesn't look good, right? It's actually doing pretty terrible. So let me actually make a function to do the sign now. Yeah, sign. So we'll have as input.
I'm sorry, I don't understand what you just did, like what the calculation was that you just did.
All it is take, so this is the inner product, right?
Mm-hmm.
And well, let's just, let me finish writing this function then. Weight at features If that's less than 0, return -1, else return +1. So if I do sine of weights, comma, let's put in feature vector 0. It's a -1. You see that? This is our feature vectors. But what is the actual label? The label for that one is a +1. So that means that our weights are not working. All it is a model. We haven't done anything to the model. Like with regression, we actually we used sklearn to fix the weights for us. What I'm trying to get to right now is that with this model, it's doing terrible, right? So like, let me just pick another vector, right? So let's see what happens. What does it predict for the 20th one? Still a -1, but it should have predicted a positive. What about 60? Predicts a -1. Okay, so it got that one right by accident. All it's doing is taking the weights that we have randomly started with, inner product with a given feature vector, and then what is the sign of that? That's our prediction. Is it currently a good prediction? No, it's not getting anything right. It's getting like half the things right. But can we fix the weights to do better? Right? Like the weights currently are doing, well, we can just count how many times we get it right. So for x in capital X, so let's say count equals 0. We can say if, so you can say I comma x and enumerate x if the sign of weights comma little x is equal to yi. Oh, let's count how many times we get it wrong. So how many times do we get it wrong? Count plus equals 1. So how many times did we get it wrong? 50. So by just guessing random weights, we got 50 of the 100 features wrong, which is terrible. That's like horrible. And that's also what you would expect from starting with random weights. Okay. So do you understand the model now? It's a model before it's been trained. Before we fix the weights, it is a model. It makes predictions and it gets 50% of them right. So does the model make do the predictions that it's making? Like, do you understand how it's making predictions right now? Right here.
I think I need a second to think about it, but yeah, mostly.
The weights are random right now. See, right here, the weights are random. And we just decided arbitrarily that we're going to make our prediction to be based off of whether or not the weights times the feature vector in question. If it's a -1, we predict that feature vector belonged to, if the sign of this inner product is negative, we predict that feature vector belonged to a -1 label. Otherwise, we predict it belonged to a +1 label. So like these are our predictions right here. But what it should be, so x40, so what's the label for the 40th one? It's positive 1. So we predicted wrong. But that should make sense though, because we just started with random weights and we haven't done anything to them yet. But we can fix these weights. We can make these weights better. Okay, and how can we do that? So let's go ahead and talk about that. I'm going to drop the superscripts for a moment just to make life a little bit easier. So we want to predict y, I guess I'll have to keep them yi for feature vector xi. We want to do that. But you saw a second ago that we were predicting a bunch of negative 1s and we should have been predicting 1s, right? So suppose we predict wrong, just like we did a second ago. We were predicting wrong all over the place, right? So then we have two cases. We predict a positive 1, but the actual label should have been a negative 1, right? That's one case. And then the other case is that we predict a negative 1, but we really should have predicted a 1, right? In fact, this is the one that we saw the most of, right? We didn't see any 1s predicted. So let's focus on that one. Let's see if we can fix that. So that's what we're going to try to fix. Our model is not working very well, and we're going to try to fix it. We keep on predicting negative 1s, but there are cases where it is 1. So let's fix it. So what does it mean that the prediction is negative 1? It means that the sign of W inner product xi, it means that that is less than 0, right? That means that the sign is less than 0. Do y'all agree? That's what the prediction is. So, but what does this mean? It means that we should have had the sign be positive. That's what we should have wanted. That's what we needed, right? We needed it for that feature vector that we fed in there, we needed it to be greater than 0. What does it mean that the inner product between two vectors is less than 0? It means that the angle between them is greater than 90 degrees. Right? It's greater than 90 degrees from what we learned in the last lecture, right? So one way to fix this is to adjust our vector, our weight vector. If we can make that angle smaller, below 90 degrees, then we got it for that input vector there. So one way to do that is to take W and add X to it. Look at how the angle went from like that to like that. You see that?
Is that always going to push it in the right direction?
Well, let's see what happens numerically. Let's look at it. So let me pull it up and let's just play with it and see. This might be fun. Okay, so currently, if you remember, it was getting like the first 50 wrong, right? Our current weights were getting the first 50 wrong. Like for example, like let's print out I. So yeah, I got the first 50 wrong. They're all negative when they should have been positive. So let's do something else. Let's say for x in capital X, let's just do what we just saw. Or actually, no, let's just do it for the first vector, right? We know if I come back up here and I do 0, we know, look at how negative that is. We don't want that, right? So what we can do is we can say, for underscore in range like 20, let's do like 10 times. Weights equals weights plus x0. All right, so done deal. So now let's look at this product.
Sorry, what does the underscore do?
It's just a placeholder for a counter. I could have put like an I there.
Oh, gotcha. Okay.
Oh, I just did it 10 more times though. Look how positive the product is. It went from -6 to 779. So we definitely fixed the weights for the first feature, like by a lot. Look how positive that is. And it predicts a 1 and the value is 1. Like we just completely fixed the weights for that one. Do y'all see that? Like look at the difference.
Yeah, so this isn't like, I don't know, like gradient descent or something where it kind of like oscillates. Like it just goes
It
positive.
actually is very similar.
Oh, really? Okay.
It's a discrete version of gradient descent.
But it's not going to bounce around, right? Like if it was negative and it's supposed to be positive, then it'll become positive, and then you iterate multiple times, it'll just stay positive forever, right?
Yeah, right.
Okay.
Exactly. So now let's look at the prediction for x1. Oh, positive. Dang, I think like it might get all the first 50 correct now. Let's see. What was it? Was it in this cell? I think I had it here. Whoa, that's so weird. That's so weird. I think so. Hold on, that just doesn't make sense to me. That can't be true. Oh, if that's true, I'm completely blown away. All right, so look at what happened here. For x in x, print. So I need the I here. I can't believe it did it. We only updated the first weight. Print. So predicted value equals the sign of weights little x. Actual label equals yi. I am just shocked that it did that. Oh, Yeah, I knew it couldn't be the case. The predicted values here should be negative. See how the actual labels are negative? I knew we overcompensated. I was really confused for a second. Yeah, see, that should have been a -1. Maybe I don't know what I was doing. I was like overthinking something, but all right. So we definitely fixed the weights for this one. But now, if we look at y of 80, right? We predict a 1, but it should have been a -1. So let's look at how we would fix that. So maybe we need to fix the weights for the other case, right? Or for the feature vector 80. So we predict, so we have sine of w times x80, the 80th one. We predict that to be positive, but it should be negative, right? But it should be negative, that we want that to be less than 0. So what does it mean if it's positive? It means that the angle between these two vectors, so if this is like x, this is w, it should be negative, which means the angle between the two vectors needs to be greater than 90. Right? So one way to fix that would be to say, look at w minus x. And then for that feature vector, maybe we'll fix that. So let's try that and see if we can fix it for the 80th vector. So, for placeholder in range 10, we're going to say weights equals weights minus x80. All right, so then let's see if we can make a better prediction.
Were we updating the weights the first time?
Yeah, we were.
Where's the code for that?
Oh, I think I got rid of it already. Because the way you'll see when you watch the video that the reason why this is so positive is because we updated it too many times. This used to be like -6 and now it's 700. So let me update 500 times for the 80th weight. I mean the 80th feature vector. And then let's see. Now it's predicting a -1. Okay, so now we fixed it for the 80th one. So for I x in range 100, if sine of weights x not equal to yi, print I just print I. But oh, not range, enumerate x. What am I doing? So now it gets all the first 50 wrong again. So we fixed the weights for the negative ones now, but now the positive ones are all. So this is how we can the problem is now it's fixed for all the ones that are -1 output, but it should be +1. So we're back where we started. So can you guess what we should do? Take any random guess. It's how we should do it. Should we focus on one and just update on that one a bunch of times, or is there a better way to overcome to like not do that?
I guess we'd need to update them simultaneously, but I don't know how you do that.
Well, we can look at one, right? And if we get it wrong, update. Like, remember when we updated the very first one, the 0th one? We updated it once and then we updated it like 15, 20 more times, right? What about if we come across one where we get it wrong, we update, and if it's not wrong, we don't do anything. And we just do that through the whole list a bunch of times. So basically,
Can you create a loop for it?
Exactly. For I equal 1 to 50, if the sign of w times xi does not equal yi, then we update our w's. And how can we do that? We can do, so here, what did we do? We added x. Oh, this is what we're, so yeah, get rid of that hat. We added x, and then here, we subtracted x, right? So here, y was +1, here, in this problem over here, y was -1, right? So we can just do this. W is equal to w plus yi times x I. Because if we predicted positive, but it should have been negative, we want to subtract off x. If we predicted negative, but it should have been positive, we wanted to add x, right? W plus y times x. Does that make sense? That way we don't have to write an if-else statement. We just look at the actual value for y, and it'll be the sign that we need to either subtract x or add x, depending on how we got it wrong. So let's do that one time for the whole thing. So we have our weights, they've been kind of skewed. So I'm going to make another one. So here are other weights. And then for I comma x and enumerate x, if sign of weights comma x, okay, if that's not equal to yi, I want to update. Weights plus equals, I'll just write it out like on the board, equals weights plus yi times x. Okay. All right, there. Okay. Let's see how bad we're performing. So count equals 0. If that, count plus equals 1. Still not doing well. That's fine though. Let's now do this a bunch of times. Let's say for underscore in range like 1,000 times or something. So for 1,000 times, we're going to run through this over and over again. There it goes. Sine of weights x12 maybe. 1. Y of 12 is 1. Sine of weights x88 maybe. -1. Weights 88. No. Y88 should be a -1. So let's try this again. Let's look at the count. So I'm also going to print I so I can see immediately. Yeah, we've perfectly got all of our weights where they should be. So now back to the picture that we had before. What are the weights that we have? The weights we have are weight 1, weight 2, weight 3. So that's our weight vector. And our prediction is this times x. And we have modified x values. We have x1, x2, 1. Because that's like our bias. That times that, plus that times that, plus that times that. Right? So our prediction is the sine of that, right? It's that inner product. Weight 1, weight 2, weight 3 times x1, x2, and then the number 1 for our bias. So if this outputs something positive, we know it's a number 1. If it outputs something that's negative, we know it's a -1. So if we write this equation out, this is a function really of if we now think of this as a function of two variables, x1 and xy, right? If we now think of it that way, we get something in three-dimensional space. Because this is fixed, that's fixed, and those are variables, we can now plot this in space, like in three-dimensional space. But our data that we looked at, right? The data that we looked at is just two-dimensional. There is no z-axis to it, right? So the data that we looked at, this is like x1, this is x2, and then here, where was our other data? The z-axis is 0, right? Like if we're trying to come out this way, the z-axis is 0. So if we want to look at a line in this space, we can just make that equal to 0 and then solve for one of the variables. So then subtract W3 on both sides. So x2 is equal to W3 minus W1 times x1 divided by, oh, that should be minus W3 divided by W2. So now we can see, so this is really like in three-dimensional space, the z is 0. So we're just on the plane somewhere. So then we solve for this variable, and it's like a function of y now. And we can plot it. So negative W3, so okay, let's share. So let's say line is equal to x, so line, maybe.
I'm sorry, could I see the board again for just a half second?
Yeah.
Thanks.
So it's going to be negative. Oh, and the indices are off. It's like 0, 2, 1 for the weights. And just let me know whenever you've got your stuff copied down.
Sorry, I got it, yeah.
Okay. Okay. All right, so now I'm just doing that. So weights, all of this. So this is like taking x1 as input. Actually, I'll even write that down. This is x2. No, I'll say it's just the line. This is all divided by weights 2. Okay. And then I'll say, I have to make like a domain to plot things. So I'll just make like range. What was my original plot? I don't know. 0 to 6 or something. Okay, so PLT dot scatter. Where did I save the? It's dumb. I'll just have to do it. X4. X in iris dot sepal length, I guess is what the first one I looked at. Sepal length, sepal width. Okay. Sepal length up to 50. And then the Y entry will be sepal width up to 50. Okay. Marker equals, I like the little plus sign. And then color equals red. And then the other species is from 50 to 100. Oh, I should probably do 51 here. 51, 50 to 100, 50 to 101, actually 101. Color these blue. And then I'm going to plot that line with that domain. Up, up, stay on page. Where'd it go? Sorry. And then PLT.plot domain, and then line of x for x in domain. Okay, and then PLT.x label sepal length in centimeters, and then PLT.y label. Hopefully this works. Sepal width in centimeters. Did I get my weights all screwed up? My weights on my line might be screwed up. Oh yeah, my weights are really screwed up, sorry. this should be a 2. This should be a 0. And this should be a 1. 0, 1. Yeah, this should be a 1. Sorry about that. There it is. Oh, I'm way off. I need to change my range here. 4 to 7 or something. Maybe 4 to 9. Okay. So there's that line. Okay. And if you recall, if you're greater than that line, you're a positive 1, which is what we gave the color red. If you're less than that line, you're a negative 1, is what we gave the color blue. Okay. Okay, so we made it. I'm sorry for all the hiccups. It was kind of difficult reading your reactions and it was throwing me off. So I'll go ahead and stop the recording there and we can discuss this.